I'm going to talk about Euler's number today in the context of mostly interest. And we're going to look at the growth of an amount given a certain amount of time and a rate by which that growth, or by which that amount grows each given compounding period. First, I'm going to introduce the key here. So whenever you see a sub 0, that means the original amount you started with, which could be like $100. In the case of a sub I, that is the amount at a given instant as you're making multiple calculations. So say you put money in the bank account and you wait 1 year and you check at 1 year. The AI is $106 if it's a 6% interest rate, like $112.36 if it's the second year, etc. Until you get to the final amount where you're actually calculating a total amount of time. That would be a sub f for the amount at the time final. Okay. Whenever you see a green parentheses here with something inside of it, that is equivalent to the growth factor. And the growth factor is an amount that you can multiply times a0, the amount that you started with, to find the amount final here. And that just breaks it down and makes it easier. So if you see green parentheses and you see it raised to a power, if you find that amount with it raised to the power, you can multiply that times a0, the amount that you started with, to get the final amount after so many years, for like interest, for example. So moving on to t, whenever you see a t, and it's usually, if not always, I guess always in the exponent, then it is the amount of time that you waited before computing the final amount, which was a sub f here. Whenever you see an orange f here, that is the frequency by which the amount is compounded. The amount of time, not the amount of time, it's actually 1 over the amount of time, kind of. So each period, if you make t in years, for example, or let's just say if the rate, which is the rate of interest, for example, if that's annually per year, then the period would be 1 year. So if the frequency is 2 and it's 1 year that 6% is being computed at, then the frequency would be 1 every 6 months, or 2, which is twice per year. So that's introducing the key here. So we're going to start out when we have a compounding frequency of 1, and I didn't write that but this is greater than 1. This is just 1. So if we just compute someone's interest annually, once a year, then we get the formula a final equals the amount you put in the bank account that you didn't touch and you left there, times, in parentheses, the growth factor here, which is 1 plus the rate. So if it's 6%, then that's 1.06 if you add those together. But you have to raise them to the amount of time in periods. So if it's a rate defined annually, that's the number of years you're looking at. So if you're looking at 2 years, for example, it comes out to $112.36. And that's by squaring 1.06 and then taking it times the amount that you started with. That makes it a little bit easier if you can just multiply it times a factor, which is why we have the growth factor here. But I'm going to want to prove this to you. That way you know why it's what it is. That's the point of this lecture. But I'm going to talk about Euler's number a little bit later in the context of infinite compounding, which means that the amount that you have the next time is compounded, but it's compounded every single moment of time. Theoretically, at every single instant, every millisecond, even less than a millisecond. Okay? So it turns out, though, you get a different amount if you're always changing the amount versus if you just change it once a year. So, and I'll get into that. And we have a little proof for you, at least if something that helps you see that we get the value E, which is 2.718281828, if you just keep increasing the amount of times you compound that per period, and then you raise it to that the number of times you compound it, which I'll get into here with the frequency, because we also raise it in the exponent there. But starting out, if it's just one time a year, so let's just say you put in, so let's find a final, right? A final equals the amount you started with, let's say it's $100 times, and then 1 plus r is 1.06, because you're taking, this is 0.06, which is 6%, and you're adding it to 1, because we want to also include this amount when we multiply it. Okay, so we're going to go 1 plus, let's just put the amount actually, 1.06, and then we are only doing it for 1 year, for example. So we're raising this to the 1 by using this formula. So, and you don't even need to think about it that way, just take 1.06 times 100, and you get $106, right? Now, what about 2 years? Let's say we do it for 2 years. Well, if we just do it step by step, we would put a parentheses here, if you want to just break it down, make it simple. That's the $106. But for the second year, what do we do at the end of year 2? Well, we're going to take it times 1.06 again, because the interest rate has not changed. If this is a constant interest rate of 6%, when we do this, let's actually break this down. This is actually the same thing as 100, which is A0, times 1.06 times 1.06. Right? That's the same thing. All we're doing is removing these parentheses, if you think about it. And these parentheses aren't needed because this is multiplication, not addition. When you're adding, though, it's not the same thing when you're multiplying, because you have to use the distributive property, or the inverse of the distributive property, in which you got to multiply this amount times this amount, this amount times that amount. You don't have to do that because this is multiplication, not addition, right? So we can break it down to 100 times 1.06 times 1.06. There's another way to express this, even if we had 3 of them, right? So let's say it's the 3rd year. We're going to have to do it again, 1.06 for the 3rd year, right? We can actually just go AF equals 100 if we're starting with $100, and we're not touching and not going on a spending spree, and go 1.06 raised to the 2. That's a simpler way of expressing this right here, right? So this also works for fractions of a year. So let's say it's 2 years and 6 months. Then we would put it to the 2.5 instead of 2. But that does work out. I'm not proving that here, but you could probably prove it with the other thing I'm going to show you a little bit later if you want, which is why I'm giving this to you to use the Google Chrome, but I'll get into that, the Google Console. So I've already shown you when you're compounding it once a year, compounding frequency greater than 1, that means that it's more than 1 time per period. And since we're defining interest rates by a year usually, we're saying if it's 2 times, for example, that's 1 every 6 months, which is a frequency of 2 per year. When we do this, we got to take the amount that we're finding, the amount that we're getting after a certain amount of time. We're taking the $100, for example, times 1 plus the rate, which is 0.06. So before it was 1.06, but we got to divide by the frequency, because if you're halfway through the year, you can't use 6%, because that would be the same as after 1 year. But this is only 6 months, so we got to take 0.03, which is half of 0.06. And 1/2, if we're putting 2 in the denominator, it's the same as 1/2 of the rate. So the frequency up here, this frequency, the number of times compounded per period, is 2. So we take the rate divided by 2, 0.06 divided by 2 is 0.03. And then we got to raise that to a power, right? Before it was the time, because it was just once a year, we just took the number of years, right? The number of periods. But now, since we're compounding more than that, and we've already divided it here, we got to look at the number of times we're compounding it, which is actually going to be proportional to the actual frequency. So instead of using just t, we're also using the frequency up here in the exponent. So we would take 2 times, if we're going to do it for 2 years, we do 2. So that's to the 4th power, right? So if we do that, let's try that once. Let's go 100 times, in parentheses, 1 plus 0.06 divided by 2, and then we put a parentheses around that. we want to raise that to, use the exponent, to the fourth, and that equals $112.55. Now, 55 cents is larger than 36 cents, so basically you got 19 more cents at the end of the 2 years if you compounded it twice a year. Here. There's another way to express this. If you want to just take the frequency times the time and just put it into the number of times compounded, you could just do n here for the number of times compounded. But this would just be the frequency here, which is the number of times per period, which would be 2. That's just a different way of expressing it. I think the actual original interest amount is, let's see, you use P for the principal, which is actually just the $100 times 1 plus the rate divided by the, I think they use N actually, I'm sorry, N is different though when you're looking at the actual interest formula. That's actually the same as frequency. I use frequency because it's less confusing because that's the number of times per unit, and frequency is actually dependent upon a unit of time. So R divided by N raised to the NT. So N is just the frequency here. That gives you the amount that you have given an amount of interest, where R is the interest rate. But now let's talk about infinite compounding. That's when you're compounding every single moment of time. And that's different because there isn't really an exact amount, right? For an infinitesimal amount, that's 1 over infinity. What value is that? Well, nobody knows because it's theoretical, right? But if we want to look at how this changes, how the amount would change for just this growth factor by itself, forgetting the amount here, let's just look at the amount in parentheses raised to the exponent, because that's where things are changing. If you take 1 plus 1 over x, and x is any amount, raised to the x, it equals e if x approaches infinity. So as long as you keep changing the number of times you're compounding it, because remember the frequency was in the denominator, so if you're making it infinity here and you're raising it to the infinity, what amount is that? Well, there's a way to at least start to see the trend that happens. So if you want, you can do this. This is optional, but you open the Google Chrome browser in a separate window. So if you do that, or a separate tab, you press Control-Shift-I. That opens up the Google console. But you see elements, console, and then something else. You want to click on console, the console tab, and once you do that, you can click in the white space there, and then you can type in some JavaScript here, which I'm showing you right here. And what this is we're basically we're going through from 1 to 9, and then we're raising 10 to that power. So when we start at 1, we're just doing 1 over 10, and then 1 over 100 the next time through the loop, all the way up to 1 over a billion, and we're doing it every power of 10. So when we do that, in order to do that, you have to type in 4, F-O-R, parentheses, and then you put in V-A-R as in variable, but just for short, I, as in Indiana, equals 1, and I doesn't have to be I, but just a lot of people in programming use I. So put I equals 1 after the VAR, and then semicolon, and it doesn't have to have a space, but you can put 1 in here, I usually do. I is less than or equal to 9, semicolon, and then I plus plus. And when you put plus plus in a loop like this, it means each time through the loop, I want you to increase it by 1. If we were to put some other number there, though, you could increase it by like 2 each time, but you don't have to. In this case, this just means shorthand for 1. Increase the number I by 1, whatever's stored in that variable, which we start out as 1 when we define this, and we're going up to 9. So up to the 9th is a billion. So we're going from 10 to a billion, but we're doing it in steps of the power of 10. We put a little bracket here. This is a curly brace, so you got to press Shift and then the left bracket key. And that's very important. Don't forget that, and don't forget it at the end. You got to put the right curly bracket at the very end. Before that, though, you put in console, C-O-N-S-O-L, .log, and this log has nothing to do with with math, this is just logging the amount that you got. So this function here, that parentheses and that parentheses there for the semicolon at the end, that tells it to print whatever the value is you put in here. And this value we want to be 1 plus, because remember we have 1 up here, plus 1 divided by 10 raised to the I. So that's 10, so parentheses after the slash, 10 star star, which is the same as the 8 button, but you got to press shift. You get the asterisk raised to the I, which is whatever the value is each time. And then you put another parentheses around that, so you have 1 slash parentheses 10 asterisk asterisk I parentheses parentheses, and then you have asterisk asterisk parentheses 10 asterisk asterisk I parentheses parentheses, and then semicolon, and then you put that little curly brace, the right curly brace there. That's going to go through, and you're basically raising it to whatever I is. You're raising 10 to that power for both the denominator here and also for the exponent. So you're taking one infinitesimal amount and adding it to 1, and then you're raising that total amount there that you just added together, and you're raising to the infinite amount. If you were just go all the way to infinity, we're only going to a billion here, but you'll see the trend is you start to see it get closer to this number, which is 2.71828, and that is E. That's Euler's number. And so the special thing about Euler's number is, you know, and it's kind of cool, but when you think about it, because it's really hard as humans to just think about an infinitesimal amount raised to an infinitesimal power. If you add 1 to that infinitesimal amount first, it's hard to imagine what that would actually be. It's kind of like you have to actually do the math to find out what it is. Well, it approaches this amount. It doesn't get any higher than this amount. That's the maximum amount you get. So if we're going to compound something infinitesimally, we're going to get into the actual formula for that. But this is a building block. You've got to start with a very small amount. No matter what the rate is, it's going to still, unless it's infinity, I guess, it's going to be a very small amount, and you're adding it to 1 and you're raising it to an infinite amount. Okay? Because remember, the frequency is what we're making infinite. And so when we multiply times the time, it's still infinity basically. So let's talk about infinite compounding here. The infinite compounding frequency can be defined by this formula. It's the amount final. To find the amount final is the amount you started with, like the $100, times 2.71 raised to the rate times the time. Now notice R here is not the same thing as F. That's different, right? So how does that work? Let's talk about it. So let's actually take this amount, let's take the rate divided by the frequency, and we're going to make that X, okay? And because it's an approximation, we're going to still use the rate here. It's a little bit of a double standard, but you can test this later. We're going to take the rate divided by the frequency. But for X, since it's 1 over the amount, right here, 1 over X, we're going to do the inverse of this value. So the reciprocal of it is, we're going to take 1 plus the frequency instead over the rate. Because that's really the same thing as 1 over R over F, but we're just flipping it around. So if you do 1 divided by the rate over the frequency, this amount here actually equals the frequency over the rate. Okay, that's how I'm getting this value here. Then we're going to raise this to the frequency over the rate, despite the fact that we only have the frequency there, because it really doesn't matter. It's usually less than 1 anyway, and it's still going to be an infinite amount. So we're just starting out with that to look at it in terms of Euler's number. Because if we could just take a constant and multiply it, that's better than having to keep doing the math all over again when we don't need to. So we end up with this value here, and that's only when the frequency approaches infinity, which is the definition of infinite compounding, okay? So when we do this, how can we get this, though, to look like this formula? Because that will be the key, because remember, this equals E right here. This is going to equal E. If we can just use E, that's way easier, right? So to do that, what do we got to do to change this side to make it look like that, but still also change this side? So when we do that, we're going to want to probably get rid of the R in the denominator, So we multiply times r and the exponent. So we're going to want to go r here, and then we're going to want to put an r here, okay, because it's because of this. So we get rid of the r, because we still have to express this in terms of rate and the time, because the rate matters and so does the time. Now, we still have to put the t in here for time. So we got to do times the time and the exponent. So we got to do the time here. Well, look at what this gives us. Now, we haven't included the original amount, so we also got to take both sides times a0, right? So we put a0 here. So we end up with this formula. We end up with $100 times Euler's number raised to the rate times the time. That's how we get that formula, okay? So does this really make that big of a difference? Well, with the more and more compounds, it makes fewer and fewer differences because it's such a smaller amount, and even though we're raising it to a higher and higher power, it doesn't make as big a difference. As you can see here, it's slowly, there were fewer and fewer differences for the next amount that you got. So, but still, it's different than just doing it one time. So I'll show you this. So let's say we have a plant that's 1 foot tall. We have a frequency of 1 for compounding. So at the end of 24 hours, that plant grows by twice its height. So it goes from 1 foot to 2 feet on day 2. Then on day 3, it goes from that 2 feet to 4 feet on the 3rd day, right? What if we're always compounding that frequency though? If we do that, we end up with 7.4 feet instead. Compare that to 4 feet. That's different, right? So it does make a difference. And if you think about it, I pick plants because plants grow, the leaves get larger, there's more chlorophyll, more chloroplasts, more sugars being created to make the plant, and the plant gets larger, and it can make more chlorophyll and more of what it needs to make more energy and make a bigger plant, right? So it just keeps getting bigger and bigger. That doesn't just happen at the end of every day, that happens at every moment, right? Although, albeit, you know, at night, maybe it grows faster. But so this is just theoretical. But theoretically, if it always grew and it was always growing larger based upon the amount that it already was, so let's say it's at 1.1 feet, well, that's 1.1 feet now that it's growing at a rate of, it's twice, 1 times its height per day. But then at the next moment, you know, or an hour later, maybe it's 1.02 or something. Then it's growing based upon the 1.2 feet now for a whole day. And it just keeps growing faster and faster and faster, right? So to find that, that's 7.4 feet. If you want to prove this to yourself, you can also use the Google Chrome browser for this. To do that, you open up the Google Chrome in another window, you press Control-Shift-I, click the console tab, and the small window that pops up. If I don't finish this, just look at what I have here and pause it and type this in if you want. Click in the white space and type the following, and it's case sensitive. You have to type it in exactly in the case that I have here. Function, growth, and then you put A for the amount, R for the rate, and then F for the frequency, T for the time. You put that curly brace in there to the right, or the left curly brace. Console.log, A times 1 plus R over the frequency, parentheses, asterisk, asterisk. This means we're raising it to a power. If it's just 1 asterisk, it's just multiplication. So it's multiplying, kind of. If you think about what an exponent is, it kind of is that. Parentheses, F times T, parentheses, parentheses, semicolon, and then don't forget the right curly brace. Press enter, and it will remember this later when you do some other stuff with it. It'll remember this function, and it will use it if you give it arguments like this, okay? Go to the next one. We're going to do continuous growth. And you also type in what I have here, which is the amount, the rate, and the time. Notice there's no frequency because we're using Euler's number instead. And we're giving Euler's number, we're going VAR space E equals 2.7182881828, semicolon. We're telling whenever you see E now inside of here, that means this number. So we're going to go console.log, which means print, whatever's in these parentheses here. We're going to put A, which is the amount that we put in the function later. We put, 100, for example, and then we put the rate of, 0.06, and we do the time of like 2 years, for example. So we're doing that here. Then press enter, but then down here is when we actually put the amount in. So we're going, first we're trying this one out, which was the same as let's see, the same as this formula here. If we use 1, it's the same as this for the actual rate, okay? In this case, we're using 1. We're going 1 as the 1 foot for the plant. Then we're doing 1 for the rate, which is 1 times its height each day. And then 1 for the frequency, which is 1 because the frequency is f. And we're doing 1 times per day. And then this is for 2 days, right? Because that's what I did down there. If you put this amount in, you put the parentheses and the semicolon here, you get 4, right? But let's try it with 1 billion instead of 1 for the frequency. So we're not just doing it 1 time per day, now we're doing it 1 billion times per day. We're checking it again and growing the amount, and we're looking at that new growth amount, and then we're using that instead to figure it out. So if we do that 1 billion times, you get approximately 7.4 down to a certain number of decimal points. If you use the continuous growth formula and you put 1 in for 1 foot, 1 for the rate by which it grows per day at any instant, and you put 2 days in, you can also get 7.4. So this basically tests what I said. And you got to press enter after you put each of these values in, because that tells it that you're done telling it what to do. When you do that, you see that this really does happen for each of those. So this, when you use a very large amount, like 1 billion, versus just using Euler's number, also gives you the same amount. So they're not much different from each other. And that's the concept behind Euler's number. Euler's number allows us to use a constant for continuous growth versus just 1 times per year or however many times you pick that's a finite amount. If you want to do it infinitely, it still gives us an amount. And that's important in science because things are always changing. And if things are always changing, you can't just say it only changes once a day. Well, it's always changing all the time sometimes. And so that's the concept behind Euler's number. I hope you enjoyed this. Thank you.